Hello everyone, and thank you for joining today's session on stability consideration, tension and compression member design using IS800 2007 code. Myself Surajit Ghosh, I am a structural engineer and I have been working in Bentley systems for more than 10 years. This is the first part of our ongoing webinar series on steel design to IS800 2007 with STAAD.Pro Connect Edition. In this series, we will cover the implementation of Indian steel design code in STAAD and also provide you some tricks and tips for efficient usage of STAAD for steel design. IS 800 2007 is the Indian standard code of practice for design of steel structure using limit state method. It is not very elaborate like AIC 360 code where almost all possible design conditions are covered. Also, there is no commentary available for this code. In this series, we are not going to discuss each clause of IS 800. Rather, we will cover the implementation of this code instead. If you want to design steel member or connection using limit state method following Indian standard, what are the variables that you need to consider? What inputs or design parameters need to be specified instead? That we will discuss in details. We have divided the whole series in 4 parts. Today, I'll cover the basic design considerations and prerequisites of IS800 code instead. This includes selection of section, load cases, combination factors, analysis methods, and other relevant inputs. Analysis method selection is one of the most important aspects which we often neglect unless there are some warnings. That's why I want to discuss about the stability analysis and how to finalize the analysis method from the outcome of stability analysis. Then I'll cover the geometric checks including slenderness and wave depth criteria check and a discussion on the section classification, which is obviously very much necessary for local buckling consideration. And finally, I'll discuss about design of axial members subjected to tension and compression force. IS 800 2007 code was released in the year 2007, and a very basic difference of this code with the previous one is the consideration of limit state method for design. In IS 800 1984, working stress method was used for design, whereas in IS 800 2007 code, limit state method or capacity based design approach is followed. There is also a section in this code, section 11, with provisions to design members using working stress method. But code suggests not to use this working stress method and use only if design using limit state method is not possible. The first priority of this code is to perform design using limit state. Note that working stress design approach in IS 800 2007 code is completely different from the old code, and it is not correct to compare the results between these two codes. In limit state method, ultimate stress value is used to determine the design capacity, which is more than the yield stress value used in working stress method to calculate the allowable stress value. So in general, limit state method is more economic, but there are several conditions when working stress method produce more economic design than the limit state method. In AIC 360 code, under commentary of design requirements, a clarification is provided when AST method is more economic than LRFD method. You can go through this section for more details. Though ultimate stress value is used for design in limit state design, still there are two partial safety factors used in design to consider the uncertainty related to load application and material property. Partial safety factor for load increase the design load value, and partial safety factor for material reduce the ultimate stress value, and combination of these two factors in design is necessary for all uncertainty consideration. In limit state method, members are designed for two criteria. One is the limit state of strength and second one is the limit state of serviceability. and it is necessary to ensure both of these criteria is fulfilled during design. Normally, strength criteria always govern the design results and section size is determined from strength checks. But it is also necessary to ensure the serviceability criteria are satisfied. There are several printing mistakes in IS800 2007 code, and all those were rectified in Amendment 1 dated January 2012. There were some major corrections like change in clause 4.4.2 or in table 2 for section classification. All these corrections are already implemented in STAAD. We have posted a detailed list of these corrections and implementation status in STAAD in our official structural forum page. The link is provided in the resource list. If you click on this link, you will be directed to the forum page where you can find a detailed report which corrections are necessary for design and implementation status of those corrections in STAAD. Though the latest version of steel design code is IS800 2007 with 2012 amendment, there is another published Indian code which provides design standard for steel member and is more updated than IS800 code. I am talking about latest NBC 2016 code. In this code, under section 6, steel design as per limit state method is described. In introduction of this code, it is clearly mentioned that this specification is in line with IS 800 2007 but more updated and improved. Some major changes are highlighted in this code. Apart from this, there are several other major changes. Like IS 800 code does not clearly mention any design rules for slender section design, but design considerations for slender section is clarified in this code. I'll cover that shortly. So, if you want to follow the most updated Indian standard for steel design, then you should follow NBC 2016 code, not IS 800 2007 code. In my session, I'll follow IS 800 code, but I'll mention if there is any update of any clause in NBC 2016 code. Instead, any hot rolled section assigned from standard steel database can be designed using IS 800 code. Standard I section or I section with cover plate, channel section, double channel section with different arrangement, angle section including double angle and star arrangement, T section are the common types of section which can be designed. Also, hollow tube and pipe sections with square, rectangular or circular shape can be designed. In latest update 6 version, design of solid rod section is implemented and this can be defined either from standard database or user-defined steel section. Apart from the standard sections, any user-defined section created either from user table or using section wizard can be designed using IS 800 2007 code. I'll cover the user-defined section design philosophy in third part of this series. In STAAD standard database, two different database versions are available for Indian code. First one is the Indian section database, which follows IS 808 1989 version. And second one is the Indian legacy database, which follows SP6 code. By default, latest database is selected, and if you want to use the older one, you can switch it from the configuration menu. Note that there are several sections which are not present in the new database and vice versa. So if you assign any section from new database and try to open that model in another computer where older database is selected, you might find a warning that the section is not available. So always cross-check the database version used in your client or contractor machine when you receive a STAAD model for review. You can also add your own custom database by importing the .db3 file with modified section property values. But remember that this custom database file must follow the standard rules and formats. Else, program will unable to recognize the sections present in the custom database file. Also, you can modify the existing database. You can change any property value, add a new section, or remove any section from the database. Once again, this change is specific to local machine, and if you don't supply this modified database along with your STAAD model, then your client is unable to use that model due to missing section or defined property values. It is better to keep a backup file of the original database for future reference. Now coming to the design loads and combinations. As mentioned in clause 3.2.1, we need to apply dead, live and wind loads from IS875 code and seismic loads from IS1893 code for design. Except these loads, there are few additional load items which can be considered for design, like accidental load due to blast or vehicle impact, ejection load which is sometimes very critical for PB structures, and also load from temperature change or differential settlement. All these loads can be applied instead, for example earthquake load using IS1893 2016 code or wind load using IS875 Part 3 code. But these loads can't act individually on any structure, and hence it is suggested under clause 3.5 that all these loads should be combined together to produce maximum effect on the structure. Load combination factors for strength and serviceability condition is specified in table 4. Dead, live and lateral load factors are specified here along with the combination factor for crane load, erection load and accidental load. Factored load combination cases created from this table should be used for design. Also, strength and serviceability combinations must be created and defined separately for design purpose. It is very hard to create all these load combinations manually one by one using relevant combination factors. Instead, there is an advanced option available to create the load combinations automatically. In this auto load combination option, you can select relevant design code, IS code for our case, and also the design category, IS800 2007 table 4. We don't have any crane load present in this model. Once you click on the generate option, all load combination cases or repeat load cases are generated considering the primary load types and combination factors specified in table 4 of IS800. You can further edit it or add it directly in the model. Now, if you want to modify any combination case or change the combination factor, you can simply edit the combination rules. You can change any value, add or remove any load case, or even create your own combination table with all your custom combination factors defined in the table. You can also copy paste the factors directly in the table from Excel or text file. And once you update this table, all modifications are highlighted in the load combination table. As you can see, my custom table is now available under dropdown. And finally, after creating the load combination cases, we need to inform STAAD about the strength and serviceability combinations. This can be specified using the load envelope option. Load envelope can be created with different types like strength, serviceability. Each type of envelope has a different purpose and program use the envelope information during design. Say you have generated load combination 100 to 150 for strength checks and 200 to 230 for serviceability checks. If envelopes are not created, then program considers all load combination cases for both strength and serviceability check, which is not correct. So, a strength envelope is generated with load combinations 100 to 150 and service envelope with combination from 200 to 230. And prior to design command, these envelopes must be defined using load list envelope command. This command informs program to consider only those combinations from strength envelope for strength design and combinations from service envelope for deflection check. In Connect Edition, it is mandatory to define load envelope before design command if deflection criteria check is performed. I'll discuss this in details in second part. Let's check the STAAD model which I want to design using IS800 2007 code. I have already assigned all sections, few from standard database and few from user table, specified steel material to all members. Gravity and lateral load cases are also generated as per the codal provisions. And finally, all factored combination cases and load envelopes are created. Next step is to fix the analysis method which can be determined using stability analysis. Do you know Indian code suggests to apply notional load to consider the imperfection in structure during analysis? Well, I have reviewed hundreds of steel structures, but in very few models, imperfection is considered in analysis. There is a guideline specified in section 4 and also in Annex B for analysis method selection. But normal trend is to perform first order elastic analysis instead and proceed for design on basis of analysis results. And if there is any warning related to clause 4.4.2, moment amplification factor greater than 1.4, then only we switch to second order analysis. Correct? Well, this is not entirely incorrect, but for accurate analysis, we should perform stability analysis. In section 4, it is mentioned that we can adopt either elastic or plastic analysis or perform dynamic analysis using IS 1893 guidelines. For first order elastic analysis, effect of deformed geometry or reduction in axial stiffness is not considered during analysis. But these effects are considered for member design using the moment amplification factors calculated under section 9. Note that there is a correction for this clause. Cy and Cz are replaced with the Ky and Kz. This is mentioned in Amendment 1 and also correct information is provided in NBC 2016. Moment amplification is one approximate way to consider the secondary effects during design, but if the value is large, then a proper second order analysis is required where additional force due to deformed geometry is calculated in iterative way. If these amplification factors are greater than 1.4, then code suggests to perform a second order analysis. So, second order effects are considered either with first order analysis plus the moment amplification factor method or by directly performing the second order analysis. You may have noticed this warning in your model. Moment amplification factor Ky or Kz is greater than 1.4. This is a friendly warning to inform the user about the violation of clause 4.4.2 and design is performed using the first order results only. It is recommended to change the analysis command to second order analysis like p delta analysis in such case, which produce more accurate results and also eliminates the warning. Now, there is another method to determine whether second order analysis is necessary or not. This is mentioned under clause 4.5.4 for two conditions. When you model the infill masonry wall or diaphragm walls using bracing system, and second one when you don't model and consider the lateral load carrying capacity of walls in your structure. In Annex B under 3.3, the procedure to model the infill walls has been mentioned. Basically, you need to model the lateral stiffness of this wall using diagonal struts, the area of which is determined from the wall height, width of bay, thickness, and also from the stiffness of the columns in that story. Depending on the elastic critical buckling factor, analysis method is selected. If the factor is greater than 10 or 20, then first order elastic analysis is sufficient, and if it is less than this, then you need to perform second order analysis. Though there is an intermediate range but that is limited to plastic analysis, hence not considered. If we perform buckling analysis and check whether the critical buckling factor is greater than 10 or not, then we can easily find out whether we should perform first order analysis or second order analysis. We know that buckling factor close to 1 means the structure is more susceptible to global buckling due to the applied load compared to higher buckling factor. So if the chance of buckling is high, then could suggest that we should go for second order analysis where the deformed shape is taken into account during analysis. For this model, to finalize the analysis method, global buckling factor is required. I have already applied the dead and live load cases and also created a combination case with factor dead and live load. This load case will be used for buckling analysis. Now, I have to assign the buckling analysis command. I am going to use the eigen method, which is more accurate. And once the analysis is performed, we can easily check the buckling factor either in the output file or in the post-processing table. We need to check the buckling factor for load case 3. Here it is. The most critical one is almost equal to 1. So for this model, as the buckling factor is well below 10, we have to perform second order analysis. So we can delete the buckling analysis command and add the second order p delta analysis command in this model. Stability analysis is not discussed properly in IS800 code. If you check any other code like direct analysis method in AISC or stability analysis in EC3 code, it covers all conditions including the stiffness reduction, local and geometric imperfection. In IS800 under clause 4.3.6, how to consider imperfection in model is mentioned. You need to apply horizontal notional load, which is 0.5% of gravity load, and this needs to be applied in each direction separately. Using notional load, you are intentionally pushing the structure in lateral direction to initiate the imperfection effect, and that imperfection will further considered in the analysis. So, in our STAAD model, we need to create two factored dead plus live load cases and apply notional load with factor 0.005, which is 0.5% of dead and live load. One in x direction and another one in z direction. Rest of the loads and combinations are similar to your normal structure. If you want to know more about stability analysis, last year we have delivered 2 sessions on this covering AISC and Eurocode. Those sessions are available in our official YouTube channel. I have included the link in the resource list. Now, the analysis method is finalized and we can proceed for design. You can select IS800 2007 code from the drop-down list and define the parameters. For each design parameter, there is a default value. If you go to Help Manual, you can find a detailed list of the default values of each parameter for every design code. If you don't define any parameter, then for design, that default value will be used. And if you change any value, then program overrides the default value with the user specified value. So don't specify any parameter unless the value is different from the default value. The first step of member design is to determine the section class according to clause 3.7 and table 2, as other design clauses to compute the capacity are dependent on the section class. In older code, section class was not considered during design, and under clause 3.5.2, a check was provided to ensure the flange and web thickness are within the specified limit. But to consider the local buckling effect, section classification is necessary, and in IS800 2007 code, section class is determined for all internal and outside elements. When the capacity is determined, we assume that the whole section is actively participating. But if any element locally buckles due to compressive load, then that weak element decreases the load bearing capacity and limit state capacity is not achieved. Hence, it is very much required to ensure there is no local failure before reaching the yield stress value. Depending on the local buckling criteria, IS code divides the section in four classes: plastic, compact, semi-compact, and slender. Plastic and compact sections can develop plastic moment of resistance, but compact section has inadequate plastic hinge rotation capacity for formation of plastic mechanism. Semi-compact section can reach yield stress only due to local buckling. Plastic moment cannot be generated in this class of section. And finally, slender section which buckles locally even before reaching the yield stress. It is the most inferior section and code does not recommend to use this section. IS800 code suggests either to use IS801 code for slender section design or reduce the section in such a way that it back to semi-compact limit. Except this, code is silent about how to handle slender section design. In NBC 2016 code, a clear idea has been provided for slender section design. This is just a comparison of the same clause between IS 800 2007 and NBC 2016. You can notice in NBC 2016, two guidelines has been provided. One is to consider the post-local buckling strength for design, and second is to reduce the compression plate width up to semi-compact limit. Along with that, two pictures has been provided illustrating how to deduct the width for pure compression and flexural compression case. You need to deduct the area and then proceed for design using semi-compact section design clauses. But for bending and shear, you need to consider that the wave is subjected to shear buckling before yielding, or D by TW ratio is greater than 67 epsilon. Using this method, code is actually reducing the section capacity by not utilizing the full section properties and indirectly recommend to use up to semi-compact class section. Instead, rectifications mentioned in NBC 2016 code is not yet implemented and only wave slender section design is possible using the modified section property method. If you assign a section with slender wave, then program reduces the wave depth up to semi-compact limit, considering actual wave thickness value, then recalculates the properties and with the modified section property performs the design. But if the flange class is slender, then program does not complete the design. Tension, compression and shear capacities are calculated, but bending and interaction check is skipped and bending ratio is set to infinity. This is intentionally set to fail the member as the design is not complete and a warning is reported in the output file informing that flange slender section design is not possible at this moment. In such case, you need to change the flange dimension, decrease the width or increase the thickness by including cover plates so that the class is within semi-compact limit. Section class is determined for all elements using table 2. For flange, depending on the section manufacture type, whether rolled or welded section, section class is calculated. The main reason for this difference is the variation in width of outside element considered for flange classification as highlighted in this figure. Now, to inform program whether the section is rolled or built up section, there is a design parameter, STP parameter. If you don't assign this parameter and design a built up or welded section, then program incorrectly considers rolled section class limits, which is incorrect. I'll discuss about STP parameter in details during compression member design. And for web of I section, three different loading condition is mentioned here: pure bending, pure axial, and bending plus axial. Note that this limiting value is wrong, and in Amendment 2012 and also in NBC 2016, correct value is mentioned. this should be greater than 42 epsilon. Instead, for each load case design is performed, hence program internally checks the loading condition and accordingly correct limiting range is selected. It may happen that for a load case wave class is slender, but for other load case it is semi-compact. So that is considered during design. If you include track to command in the output file, section class of the critical section is provided, both for flange and web, as you can see here. Now, why the section class of critical section is only provided, or what is the meaning of this? To understand this, you need to attend the third part of this series, where I will discuss how to interpret the design results from the output file. There is another criteria mentioned in the code to limit the web thickness under clause 8.6.1. For each member or plate girder, the web thickness is limited considering the serviceability requirement and compression flange buckling requirement. For serviceability requirement, using clause 8.6.1.1, program checks the d by t ratio of web depending on the transverse and longitudinal stiffener information, and for flange buckling requirement using clause 8.6.1.2, once again the web depth to thickness ratio is checked. If any of the criteria is not fulfilled, then a warning message is reported in the output file indicating the violation of the minimum web thickness criteria. As this is a serviceability requirement, so design is not terminated, but to eliminate the warning, you need to modify the web, either increase the web thickness or strengthen the web by adding the stiffener. There are three parameters which control this web thickness check, and these are required to specify the longitudinal and transverse stiffener information: LST, TST, and TSP. These are the three parameters. By default, program considers that no stiffener is provided, and if you want to change, you need to specify these three parameters. After section classification, the first check which is performed is the slenderness check. It is performed for both major and minor axis, considering the relevant R value and the effective length value in that particular axis. And this ratio is compared with the slenderness limit provided for tension and compression load. If the limit is crossed, then member fails in slenderness and same is reported in the output file. In IS800 code, under clause 3.8, table 3, the maximum slenderness ratio is mentioned for different conditions. For example, the ratio is limited to 180 for compression member under dead and live load and 400 for tension member. There are other conditions also, and you need to fix the slenderness limit from this table depending on the loading condition. Instead, there are 6 parameters which controls the slenderness check. Ky and kz are the effective length factors, whereas ly and lz are the effective length for buckling in respective axes. By default, effective length factor is considered as 1 and member length is considered as LY/LZ value. If you want to change the effective length, then either specify the factor using Ky or Kz parameter, or change the LY/LZ value by multiplying the actual length with the length factor. Main and Tmain parameters are used to specify the slenderness limit for compression and tension force. Their default value is 180 for compression and 400 for tension. You can change the limit by specifying these two parameters. Also, if you want to bypass the slenderness check, specify the main and Tmain parameter as -1. Then program skips the slenderness check and no results for slenderness is reported in the output. In general, the actual length K and L value along with the actual and allowable ratio is reported in the output file. But if you skip the check, ratio values are reported as 0. In this context, I want to mention another important design philosophy followed in STAAD. STAAD performs design for each member at 13 sections for each load case. It may happen that for one load case, this member is under tension, and for another load case, same member is subjected to compressive force. As STAAD performs design for each load case, so program checks whether the member is under tension or compression for design load and accordingly calculates the slenderness ratio considering the limiting value for that loading condition. And among all those calculated ratio values, the critical most is reported in the output. So you don't have to worry about the force reversal. Program internally considers that during design. I'll discuss about this design philosophy in next session. There is a small change in design routine in recent STAAD version for slenderness check. Previously, if the slenderness ratio was less than 1, then it was not considered for critical ratio calculation and only strain check ratio were considered. This means if the highest ratio from strain check results is zero point 0.6 and slenderness ratio is zero point 0.8, then also critical ratio was reported as zero point 0.6. But now this philosophy has been modified and slenderness ratio is now considered for critical ratio calculation. For same case, in recent version, the critical ratio will be reported as zero point 0.8 with critical condition as slenderness. So if you compare the results with older version, you can find a ratio mismatch. Don't worry, just compare the detailed ratio table. Note that if member fails in slenderness, then both in older and new design routine, same ratio is mentioned in critical ratio, there is no change. Now coming to strength design, the first one is design for axial tension. The basic principle of limit state is to calculate the section capacity and compare that with the actual factored force. Though we consider the ultimate stress value, but it is reduced during capacity calculation using material safety factor, which considers the variation of material properties from characteristic value. Also, the load is increased using combination factor as discussed earlier. For tension member design as per section 6, tension capacity is calculated based on clause 6.2, strength due to yielding of gross section, 6.3, strength due to rupture of critical section, and 6.4, strength due to block shear. The minimum capacity value among these three is considered as the tension capacity of the member. A tension member can fail by reaching one of the two limit states, excessive deformation or fracture, and the objective is to prevent this failure before reaching the ultimate loads on the structure. Steel members without bolt holes can sustain loads up to the ultimate load without failure. However, if the force in the member is high enough, members will elongate considerably at this load, and this permanent elongation may reach up to 10 to 15% of its original length. Permanent deformation is not a desirable state, and at this stage, member may become non-functional due to excessive elongation. This is considered as a failure, and capacity for yielding of gross section is calculated using clause 6.2. Second type of failure, which is the most critical for any tension member, is the rupture failure at critical section. This failure normally occurs at the location of connection where the member is connected with another member or gusset plate. Consider section AA, which has a gross area of B into T. T is the thickness of the plate or the member, and capable to sustain the applied tensile force without failure. At section BB, there are two bolt holes due to which effective area is reduced. This reduced section, or what we called as net section area, is not sufficient to carry the tensile force. Holes in member cause stress concentration at service load, and when load is applied, this weak section tears apart as you can see here. Now, depending on the bolt arrangement, there might be multiple critical sections of failure in rupture. For rupture strength calculation, the net area is required, which can be calculated by deducting the bolt hole area and adding the strength gain in diagonal line for staggered pitch. Instead, this equation mentioned under clause 6.3.3 is used for rupture strength calculation. And finally, there is another tension failure which is a combination of tension plus shear failure. This failure normally occurs at the connection zone, and similar to rupture failure, it has multiple failure paths as you can see from this figure. Block shear failure is a limit state that combines tension failure on one plane and shear failure on the perpendicular plane. When the connected members are pulled due to tensile force, one plane reaches ultimate strength, the other plane develops full yield. Therefore, two possible failure modes can develop. First, rupture occurs along the net tension plane and full yield develops along the gross shear plane. The second failure mechanism assumes that rupture occurs along the net shear plane while full yield develops along the gross tension plane. In clause 6.4, these two conditions are mentioned and minimum capacity is considered for the block shear strength. There are 8 parameters which controls the tension design. Alpha parameter is used in clause 6.3.3 to define bolt numbers for rupture. AVG, AVN and ATG, ATN are used for block shear check. FU and FYLD are the ultimate and yield stress value of steel. And finally, NSF parameter is used to calculate the net section area. It is a factor which by default considered as 1, means there is no reduction and net area is same as the gross area. If there are bolt holes, you need to calculate the net area or deduction due to bolt holes and accordingly specify the value of NSF as a factor. In similar way, you also need to calculate net and gross area for block shear. Note that by default, block shear check is not performed. If you specify area values in these 4 parameters, then only program performs the block shear check. As STAAD does not have any information of connection during member design, so these parameters cannot be automated and needs to be provided manually. For tension design, in the output file, inputs like FU, FYLD, NSF and alpha values are reported and also the critical force and capacity values for yielding, rupture and block shear is reported. Critical load case number is also printed. If a member is not subjected to any tensile force for any load case, then also tension capacity is calculated, but the actual force and load case are reported as 0 and overall tension ratio is reported as 0. That's all from my side today. Hope to see you all in the next session.